All right, bit shorter lecture this week with lecture 11 on geologic structures and formations. We're going to touch on some of the things that we've covered briefly in past lectures, such as faulting, and get into a few new large-scale formations, such as anticlines and synclines, all surrounding the same kind of forces that we've gotten into before. So, geologic structures are any kind of large-scale geologic feature evidenced by a specific pattern or arrangement of rock or sediment otherwise. These structures are produced by large-scale events or forces and include clues as to how they came to be. This gives rise to the subsector of geology referred to as structural geology. It's the study of all of these particular arrangements and how they indicate certain events in the past. Large geologic structures come from large geologic forces, and most of the time when we're talking about large forces within the realm of geology, we are either speaking directly of plate tectonics or of something that results from plate tectonics. Sedimentary structures are the exception to the rule. We've gone over this before, and we know that those form via small forces, such as wind and water currents, small critters burrowing in the sediment, or mud cracking, just as a few examples. Everything else, those which occur on a large scale, are a function of tectonic activity. Reminder from our previous discussions that there are three principal types of stress, and that's based on their direction relative to the object experiencing the stress. Those are compressive, tensional, and shear. Compressive is where it's being compressed or pushed together, tensional being torn apart, and then shear moving back and forth, frictional. If we're talking about the interaction between tectonic plates, it becomes convergent, divergent, and transform. Directionally, all the same thing respectively, just at a different scale. Now, strain is the result of stress. So in all of these images where you're seeing the before and after, strain is the after picture. Those arrows are the stress, but the actual changing of that shape of the body that the force is exerted on is the strain. This principle can be applied to large-scale geological features by looking at that strain or the exhibited change and then interpreting what stresses would have acted upon that body to produce that strain. Now, of course, unlike in these diagrams here, we don't have that before image. We're just looking at the after. So you have to start with some base assumptions, those being around the principles of original horizontality. Recall that that is the assumption that everything is deposited flat and laterally continuous. The other key concept in making that interpretation is understanding that different rocks will behave differently when subjected to stress. Now, this depends A, on the type of rock, and also B, on the environment that the rock is in. And the thickness of the rock body can be an additional component here. For example, it takes much less stress, applied stress to snap or deform a twig than it does to snap or deform a branch. And that's because there's physically more molecular bonds to break through. And you need more energy or more stress to break more bonds. What happens when you're trying to break that branch for your fire and you've got it propped up on your knee and you're pushing down hard as you can on either side and you're pushing harder and harder, you are applying an increasing stress to that branch. And with increasing applied force, you're growing closer and closer to the stress capacity of that branch. When you finally hit that stress capacity, the branch will break because it simply cannot withstand any more stress. Keeping with the same analogy, if you were to pick up a twig that's not been seasoned, meaning it's not dehydrated, it still has that moisture content, it's been broken off of the tree recently, and you bend it to a certain point and let go, it'll probably bounce back to the point where it was at before, retaining its original shape. In that case, the the twig is behaving elastically, elastic response to stress. Just like a rubber band, stretch it out, let go, it snaps right back to its original shape. That is an elastic behavior. However, that twig is still going to have a stress capacity. So if you keep bending it and bending it and bending it, turning it in on itself, eventually you're going to reach the elastic limit. That is the stress capacity of something that normally behaves elastically, but when you apply a certain point of stress, you reach that capacity, then it will deform permanently, or in this case, the twig will break. You do the same thing with the rubber band. You stretch it too far and it snaps, it's not going to go back to its shape, it's broken. It has reached its elastic limit. We rarely see elastic behavior in rocks, just because of the durability of rocks and their hardness. We can sometimes see this in liquid rock, lava, or magma, although even then it still doesn't occur that often, because in order for an object to return to its original shape, that stress has to be removed, and there's not a whole lot of geological situations where stress is going to be applied and then removed. What we see far more often in rocks is that brittle behavior. This is the snapping of the dried twig. Very easy, very low force, permanent damage almost immediately, very low stress capacity. Brittle, just like peanut brittle, just snaps into different pieces and chunks. A ductile response, or ductile deformation, is something in between elastic behavior and brittle behavior. So this is when exposed to an applied stress, a rock body will deform or change shape in some way, reflecting the direction of the stress or force, but will not return back to its original shape if that stress is removed. It also won't break. It won't fracture into different pieces. So you can think of this like taking a ball of Play-Doh and twisting it up into a different shape, any shape you like, but without ever actually tearing the Play-Doh. Of course, when you let go of it, it's not going to go back to that original ball shape of Play-Doh. Folds are the geologic manifestation of ductile behavior. These are wave-like structures or bends in the rock layers, usually as a result of compressional stress. You can see an example of this in the top right corner there. If you can picture, the applied stress to this body would have been on the left and right side of that box, pushing in towards the center. If you lay a piece of paper flat on your desk and put your hands on either side and slowly push in towards the center, you're going to end up with wave-like structures, just like in this picture. And chances are you've never really seen a formation like this before, so there's a picture there in the bottom right of what that actually looks like. We don't really get these a lot in Michigan because this happens with hard rock or bedrock, and we have a lot of loose glacial sediment everywhere. So this really only happens when we have bedrock at the surface, because if you were to apply these same forces to sediment, it would just shake out. It would be like stirring a pot of sand. Now, bringing your attention back up to that top figure, there are a few vocab terms here, one being the hinge line. The hinge line is the line along which the fold actually occurs. When you're in grade school and you ask your teacher, are we folding this hot dog or hamburger? What you're asking about is what direction is the hinge line. It's the actual line of that fold. That hinge line is a one-dimensional feature across that fold in the direction of the fold. The axial plane is a two-dimensional feature where we're basically slicing right along that hinge line. So that's that blue slice through that, or those blue slices through that top figure there. This is what splits any given fold into its limbs. So a left limb and a right limb, or really you can think of these as halves. So in this same case here, we actually have 6 limbs between 3 folds, because each fold will have 2 limbs, even though because there's a fold in the middle of 2 folds, 2 of those limbs are shared. So the left limb of that center fold is also the right limb of that left fold. Now, because this happens at a large scale, we see these happening in waves, so there are a lot of peaks and troughs or ups and downs. So that language, as you can see, gets kind of complicated rather quickly if you're talking about it that way, which is why we have the terms anticlines and synclines. Anticlines are the upward pointing folds, and synclines are the downward pointing folds. This is pretty easy to see if you can see the whole fold, the full up and down, or if you've got a good side profile, an outcrop, a cut through those layers. But what if you're looking at an eroded surface, say just this part right here? Then what? Well, if it's a syncline, we'll see younger rocks exposed at the top. And then if it's an anticline, we'll see older rocks exposed at the top because of that erosional surface. One easy to remember this is that that first part of syncline is sink, and so I'm thinking that it's sinking into the ground. It's the bending downward. And then with anticlines, you can think of just the shape of the capital letter A. It's that pointing upward. The other element to look at here is the symmetry of the folds relative to one another, or their individual dip angles. How slanted are the limbs? Are they equally slanted? So if we look at this example right here, this is a symmetrical fold because there's the axial plane is straight up and down. That would be a dip of 90 degrees, and its limbs are equal in terms of the angle between the dip of the beds, which way are they dipping. So it's the same angle here as it is here. An asymmetrical fold is where we have the axial plane dipping at some angle greater than 90 degrees, giving it limbs with, giving it limbs with two different dip angles. So this angle would be greater than this angle. This angle here on the right side with this one is a much tighter angle, or at least a little tighter angle than this left limb. If that becomes a degree which exceeds about 130 degrees, we call it an overfold, or sometimes referred to as an overturned fold. If that approaches 180 degrees, then it becomes a recumbent fold. And what these different angles of deformation show are the different angles of applied stress. So for this one with a perfectly straight up and down 90-degree axial plane, the principal direction of stress would be straight horizontal, because the direction of applied stress is perpendicular to the fold plane. So this would be straight left and right in this case for this kind of fold to be produced, whereas in this case, the direction of stress would be at an angle relative to the surface, so that we end up with this further curved angle, and then it just continues with being perpendicular to that axial plane, and then the further we go, the more it becomes flattened. So in this case, it's nearly straight up and down. If that angle is very low, then we end up with an open fold. This is kind of like a very gentle dip in the landscape, or gentle rise, but it's still a fold. On the opposite side of that spectrum, when the folding is very tight, notice the penny in this picture, we call it isoclinal, or sometimes referred to as hairpin folding. And last but not least, we can have plunging folds. So plunging folds are where the hinge line is not horizontal, meaning that it is not horizontally floating above the flat plane of the landscape, but rather plunging into it. When that happens, we end up with something like this. It's those same folds that we would see on what would be a flat up and down face towards us, but instead it's flat on top of the land in like an aerial view. Basins, which you guys are already familiar with from our Michigan geology lecture, are sometimes referred to as doubly plunging synclines because if you look at it, it can be considered to have two hinge lines pointing inward towards each other, those plunging hinge lines specifically. Domes are the opposite side of this coin and are sometimes called doubly plunging anticlines. It's where those structures or the beds dip away from a central point rather than towards a central point. So it's pointing upward. It is the convex mirror that you see at the end of the hallway. It's that convex mirror of the land, whereas the basin is the concave contact that you're putting on your eye. I guess that one could be convex or concave depending on which way you're looking at it, but the dip down, a soup bowl. There are two main types of fractures in rock. Fractures are just any kind of breakage that is permanent. So this is the result of that brittle behavior. It's reached its maximum stress capacity. And those two types are faults and joints. You guys are well familiar with faulting by now from our earthquake and earthquake hazards lectures. These are the result of large applied forces, and depending on the direction of stress, it'll either be a normal, reverse, or strike-slip fault. The normal faults are a result of the compressional, reverse are a result of the tensional, and strike-slip are a result of the shear. And all of those types of faults serve to release the internal stress. It's reached its stress capacity, it's breaking, and in that breakage, it relieves that stress. Another way to relieve that internalized stress is to joint. And a lot of times we'll see this as parallel features in bedrock. So it's like a lot of straight faults or fractures parallel to each other, all in the same direction. Now, sometimes we can have multiple where it ends up looking like a checkered board. And then we can also have joints resulting from compressional stress, or excuse me, contraction. And contraction is special. It's another subsector of stress that we don't generally go over. It's what causes specific types of jointing because it is both compressional and tensional. One example of this is the formation of columnar basalts. These are these Minecraft-looking figures. They're very common in areas with flood basalts. Those are very laterally encompassing igneous rock flows. So the lava spilling out onto the land for very large portions. The basalt flats out west are an example of this, covers several states. The Columbia River basalts. And so when these cool, they contract, and that contraction is both compressional, but because the entire body is compressing into a smaller confined space, but at the same time that shrinking is tensional because it's pulling itself inward. With this example of the columnar basalts, what happens is that these cooling centers, marked by a C in this diagram, will randomly propagate through the cooling body of lava. And then all of everything that is equally spaced from each cooling center will start to pool inwards towards that cooling center that it is closest to. And this results in the formation of these hexagonal blocks or prisms that extend downward for the whatever depth or thickness of that lava flow. So we get these really interesting looking structures in a few different places around the world. What we didn't cover last time when we talked about faults are horst and grabens. When faulting occurs, it's a result of some sort of major force or geologic event, which means that we're not usually going to have just one single fault. We're usually going to see a series of faults among the area affected. We can look at them then individually or as a group. So take a look at this diagram here. With these individual faults, you see a hanging wall moving downward and the foot wall moving upward. So this would be a normal fault here. Both of these would be. But we can look at it as a full structure, in which case this middle section here that is thrusted up in this process is referred to as the horst. Now these arrows are showing the overall applied force to this body. If we take the same kind of fault, see this is still the hanging wall moving downward with the same applied stress, but it's flipped directionally. Here we can see it dipping this way, and here it's dipping this way, although they're the same fault, same type of fault, and same applied direction to the overall structure, then because of that angle difference, we're going to end up with a graben, which is where that center chunk of land will move downward rather than be pushed upward. And in this case, it's not so much the center being pushed upward as it is the opposite sides falling downward. Orogeny is a time period of extreme land deformation. Mountain building is one type of orogeny. And mountains are the result of convergent plate boundaries. That collision of crustal material is going to create a bunch of folds and faults as those two pieces of earth smash into one another, and they'll form those folds and waves and faults that we've just looked at. That's why we see mountain belts or linear formations of mountains along convergent plate boundaries, or where convergent plate boundaries have been in the past, keeping in mind that all of these plates move around and our continents have moved around over the existence of the Earth. The greater that convergent force, the taller the resulting mountains will be. And it also depends on the type of crustal material. So if it's oceanic and continental, we're less likely to get very tall mountains because the overall thickness, that oceanic underneath that continental, is going to be less thick in comparison to the continental convergence. That's where we get our tallest mountains, because that's just more material being smashed into each other. And the more applied force there is, or the greater amount of material there is, the sharper those mountains become. Now, when we see something very sharp and pointy, like this example in the top right corner here, or the mountain that the Grinch lives on in The Grinch Who Stole Christmas, those types of things are a function of both that original force creating a sharper feature, and then more so really glacial erosion. So as that ice and snow cycle of melting and refreezing and carrying away material down to the lower elevation points, it will eventually sharpen the land into these fine points. This is just a visual summary for you guys. I like this figure because it organizes things in terms of the applied stress. So you have the applied stress up here, compressional, tensional, and shearing, but then if you look at it this way, it's folding or stretching or shearing in a ductile behavior. So the second row is all ductile, whereas everything in the third row is a brittle behavior. That's where you get your different types of faults. And if you have a print of this, what you should go ahead and do is add the type of fault that you're seeing here. So reverse, normal, and strike slip. So that's it. Fairly short lecture, as promised. A few reminders per usual for you guys. I have commented and on your research project posts whether or not it's been approved, and if there's a caveat with that. Most of the comments that I left require a response, so please go look at those. That way you know if your topic has been approved or if you need to take a slightly different direction, make some tweaking. Some people didn't select a presentation format, so you need to tell me what it is that you're thinking with that. And then if I just said topic approved, please still respond just so I know that you did look at it and we're on the same page. And then, per usual, take the lecture quiz, and then over break, please do something nice for yourself. It's a time to be thankful and a time to rest and restore, which is why we don't have lab this week. All right, you guys have a good holiday, and we'll see you next time.